In today's video, we're going to look how to sort using insertion sort. So this is the array we're going to sort. The Java code for today's video can be found in the description below. So the first pass, I'll show you how to sort it using an extra array. In the second pass, I'll show you how to sort it in place. So let's look at the first way. So the way we are going to do this is we're going to take elements one by one and insert them into a sorted array, which is this array. So right now it's empty. Okay, let's start. Take 7, insert it here. Take 1. Start from the left, compare. 1 is smaller than 7, so this is 1's position. Move all elements by 1. Okay, next element. Again, start comparing from the left. Bigger, 9 is still bigger, comes here. Take 0, start comparing from the left. Okay, 1 is bigger than 0, so this is 0's position. Move all elements by 1. Okay, so now it's sorted. But in this case, we used an extra array. Now let's see how to do it in place without using extra array. So here, instead of using extra array, we are going to have an imaginary boundary with this red. Okay, so right now, anything to the left of the red is sorted, right is unsorted. So right now, everything is unsorted. So first, move it one element. Okay, now to the left, everything is sorted. Now I move it one more. So the way you do it when you move is you compare it with the elements on the left and you swap it if this is smaller. So in this case, 7 is bigger than 1. I swap it. Okay, this is sorted. Now I move it here. Compare it with the element on left and swap it as long as you need to swap. So in this case, 9 is already bigger than 7. No swapping is needed. Move it here. Okay, 0 is smaller. Swap. 0 is smaller. Swap. 0 is smaller. Swap. Okay, now it's sorted. So the thing to remember here is if this is an already sorted array, it's going to be much faster. So let's just see. Now, right now it's sorted, right? Suppose I start from here. I sort everything to the left is already sorted. Okay, right is unsorted array. Move it here. There is nothing to compare 0 with. Move it here. Compare 1 to 0. It's already bigger. No need to do anything. Move it here. 7 is already bigger than 1. No need to do anything. 9 is already bigger than 7. No need to do anything. So in this case, we just touched every element once it's already sorted, which means big O of n. So for an already sorted array, which is a best case scenario, the big O for insertion sort is big O of n. But in a situation where most items may be unsorted, or all of them might be sorted in the reverse order, like something like this, in that case, it is big O of n square. So let's see that also. I move this here. In this case, nothing to do. Move it here. 7 is small. Swap. Okay. Move it here. 1 is smaller than 9. Move it here. 1 is smaller than 7. Move it here. Next one. 0 smaller than 9. Smaller than 7. Smaller than 1. So practically, for every element, you might have to swap it with up to n elements. So for n times n, for n elements, you might have to swap it with n elements. So that's the worst case scenario. So big O of n, so insertion sort worst case scenario is big O of n square. Average is also considered to be big O of n square. Best case scenario, when it's almost sorted, then it's big O of n. That's all there is. Thank you.